let's look at this one. So when we add together, we get 2 hydrogen gas, 1 from each equation, plus 3/2 oxygen gas, yields H2O liquid, well, H2O2 liquid, plus H2O liquid. Did you all get the same thing?
We multiply everything by 2 and then multiply the H0 by 2 to get rid of that fraction.
Oh, good question. I don't like fractions. Can I multiply this and get rid of it? Certainly you could. What does that do to the heat? It's going to double the heat too. So would it still be a good thermochemical balanced equation? Yes, it would be. So could you do that if you have an aversion to fractions? Yes, you could. Can you get away with doing that in your fraction aversion all the time? No. In about 10 minutes, you're going to hit the situation where you have to suck it up and deal with fractions. Okay, but that's only one very specific situation, and we'll talk about that. All right, so first we're going to talk about Hess's law of heat formation. And Hess's law says this, that if you do something in steps, the energy is the same as if you did it all at once. So if we're looking at the energy I use to walk the length of my leash, then we could calculate how much energy I used. But if I do it in steps, where I go this far and stop, and then I go down to here and I'm traveling the same distance, we could take the energy from each of the steps and add them together, and it would be the same as when I did it all in one step. And that's a really useful situation for us in chemistry, because there are times that we are not prepared to or cannot do a reaction for whatever. Some of you are going into engineering. So if you're going to build a plant or build some equipment, you better know how much heat's going to be built up in that chemistry that's going on or in the process of production, whatever, so that you can provide adequate cooling. And it would be useful if you didn't have to run the experiment one time and see how much heat there was and not be able to contain it. Okay? I observed what happened once. I was working for profit before I started teaching, and we had an incident where a reaction ran away and generated so much heat energy that it actually blew the wall out of the building. So that was not a good situation. Okay? So you want to avoid that, and that's why Hess's law can be so useful. So here's the rules. When you're looking at these problems, if you turn an equation around, you reverse it, we change the sign. If we change the coefficients, we change delta H the same way. In order to cancel things from both sides, they have to be in the same physical state. Because if you have water liquid and water gas, they're in different physical states. They have different energy for that physical state. So we can use Hess's law to find standard enthalpy changes for reactions that are not convenient to perform in the laboratory. So let's look at the first example. Calculate the delta H for the preparation of iron 3 oxide according to this equation. Delta H0 is unknown. And we're given this information. We know that iron 3 oxide reacts with carbon monoxide to make iron solid and CO2. And we know carbon monoxide and oxygen react to make carbon dioxide. So when you look at these problems, it's kind of a puzzle. We think of it as this is our target equation. I want to make this equation. And how can I make this equation from these pieces? So you look at all the pieces in your equation, and then you look for those same pieces in the same place in the other equations. So let's just start off with this one. I have 1 mole of iron 3 oxide on the product side in my target equation. So I'm going hunting in my 2 data equations to say, is there any iron 3 oxide in there? And yes, here is some iron 3 oxide. I need 1 mole on the right. I have 1 mole on the left. So the first thing I'm going to do to get this piece where I want it is to turn this around. So I can say 2 iron solid plus 3 CO2 gas yields iron 3 oxide, there shouldn't be a parentheses in there, plus 3 carbon monoxide. And because I turned it around, I changed the sign of the enthalpy term. So I now have a positive 26.7. These all have units of kilojoules. Now when I look at this, I have this piece where I need it. And I also got lucky. I now have 2 moles of iron where I need it. So that worked out with one equation. But when I look at this, I've got carbon dioxide and carbon monoxide in there that I don't want in there. So we're going to have to deal with those as well. So now, if I look at the other piece that I need that I don't have, I need 1.5 moles of oxygen. So if I look at this equation, it has half a mole of oxygen on the left-hand side. So I'm just going to multiply this whole thing by 3 and see if that helps me. So I now get 3 carbon monoxide plus 3/2 oxygen gas yields 3 CO2 gas. And delta H0 for that, I multiply the number I had by 3, negative 849.0, with units of kilojoules. So remember, in this chapter, again, really important to put those subscripts in there. Now I have the 3/2 oxygen that I need. So when I look at this and add it all together, I have 3 carbon monoxide on the left, and over here I have 3 on the right. So I can cancel 3 moles of carbon monoxide. I have 3 moles of CO2 on the left and the right, so I can cancel those. So I lucked out that everything canceled with those first 2 equations. This was a pretty simple problem. So now what's left is 2 iron solid plus 3/2 O2 gas yields Fe2O3 solid. And my standard enthalpy change is just these 2 numbers added together, 26.7 and negative 849. So I get negative 822.3 kilojoules. I follow the rules for addition, preserving the place. So this was on a scale of 10 for difficulty, this was a 1. Okay? This was the simplest problem because we only had 2 equations to manipulate and we got exactly what we needed and everything canceled. Now, as you're doing these, you may see problems. The next one for you, I would guess it's about a 4 or a 5. And I'm going to have you try that one on your whiteboards. Sometimes you'll see problems that have more equations than you need. And so you may not use all the information that's given. Don't let that alarm you if you see some homework problems where they give you more than you need. Those would be like 4s and 5s. At the very end of the chapter, we're going to have a 10. Okay, go ahead and do the next one on your boards with your groups.